Let's take a look at another example of the constant velocity particle model with a graph and writing the mathematical model. Okay, so we see here a graph I'd used in a different video, so I already talked about finding the equation for the orange line. Next, let's do it for this blue line. So we're going to do the same formats. Remember, y equals mx plus b, because this happens to be a linear relationship. When we see nonlinear relationships, of course, we're going to use a different base equation. And so we start with what's on the y-axis. Position is on the y-axis. Remember, use x for horizontal position. We will use y for vertical position, but right now we're just working with horizontal. And then on the x-axis, we have time. So we're going to put in t for the x. B up here is our y-intercept. So let's take a look at where the x-axis is 0, follow that up, the y-axis is 3. So what that means is that when time equals 0, when we started the stopwatch, our buggy or whatever we're looking at was already at the 3-meter mark. It was 3 meters away from the origin. Now, here's where things get fun. So we see this line is downward sloping. That should tell you that this is going to have a negative slope. That's very important to not forget the negative. So let's take a look at the slope. So the slope is going to be rise over run. But this case, instead of going up, we are going down. Okay, so in this case, the rise is not so much of a rise, but a decrease. So that's very important. So in this case, when we're looking at the rise, for example, here, I'm going down 3, 2, 1, 0. So I went down 3 meters, or the rise is a negative 3 meters. Okay, I went 3 meters backwards, going down the y-axis, and then going over on the x-axis. That gets me to 6 seconds. So 0 to 1, that's 1 second, 2, 3, 4, 5, and then 6. Okay, so our run then is going to be 6 seconds. So again, make sure you have that negative sign on, indicating that our position is decreasing as time is increasing. And so we see here, this is going to be a negative 1/2 meters per second. Now in math class, they ask you usually to leave it as a fraction. In physics class, remember, we like decimals. Now 1/2 is pretty obvious what that is. If you really want to leave that as a fraction, you can, because we all know what 1/2 is. Or you could put it as a negative 0.5 meters per second. Now remember where that meters per second come from. The rise is on the y-axis, so we put in the negative 3 meters because that's a unit on the y-axis. And then the run is 6 seconds. So the time, our variable, is equal to 6 seconds at that point, or a change in 6 seconds. And seconds is our unit from the x-axis. So that turns into meters per second, or our velocity. All right, and remember what that negative sign means here is that our object is moving in the reverse direction. So it's headed back towards the origin as opposed to moving away from the origin in this case. All right, so let's take a look at making some predictions. So I put our mathematical model, or our equation, at the top. And so let's look at some of our questions. Where will the buggy be located 4 seconds after it started? And where will the buggy be 10 seconds after it started? So go ahead, pause the video, try these out on your own, and then come back and check to see if you're on the right track. All right, so let's try solving these together. So where will the buggy be located 4 seconds after it started? So it started here at 0 time when the stopwatch started, and here it's at 4. We go ahead and follow that up, and we could always estimate that and say, yeah, that looks like about 1 meter. But let's go ahead and plug in the equation. Since we do have the equation, then this will give us a more specific prediction here. So we're just going to go ahead and plug and chug things in. So first, it's always good to rewrite your equation under the question that you're answering, so everybody knows what you're using to answer. It's going to be obvious to you, but it might not be obvious to anybody grading your paper. Usually me, but in the future it could be other people when you go and take future classes. Okay, and so then we're going to plug in our time. So I plugged in 4 seconds here for t, and now we're just going to go ahead and solve. So we take 4 seconds times negative 0.5 meters per second, and notice here seconds and per seconds cancel. So we're going to be left with meters on this side, and we're adding it to something else with meters. So that's very important. When we're adding or subtracting, our numbers need to have the exact same units on them. So we end up with -2 meters plus 3 meters. This is where that negative is important because this now becomes 1 meter. If you forgot the negative, of course, you'd say 5 meters, and that doesn't make sense. So 4 seconds after the buggy started, it is located 1 meter away from the origin. So it went from 3 meters position down to 1 meter. So next, let's take a look at where it will be 10 seconds after it started. So we see our data here ends with 6, and we could keep extending our line, except we have run out of grid paper here. There is no more graphs, so we can't extend out the boxes. I know a lot of you guys like to try to draw in your own boxes. It's not going to work because those are not going to be very accurate. All right, so this one we have to use our equation. And once again, I write out the full equation here. I know that gets annoying after a while. Just do it because that's going to help, again, whoever's looking at your work know exactly what you're doing, what's going through your mind. And then we plug in 10 seconds for t. Once again, we notice that those seconds cancel. So I end up with -5 meters plus 3 meters. Okay, so what that means is that the buggy has moved 5 meters away from where it started, and it started at 3 meters in front of the origin. Now we get a -2 meters. Like, well, what does a negative mean? So that negative sign just means that it went to the origin and then went past it. So we could say it's 2 meters behind the origin would be another way to phrase that. So remember, sometimes it's just kind of arbitrary where we set our origin at, and then we're just going to measure everything relative to that origin. Okay, hopefully that made sense, and let me know if you have questions.